Hi everyone. Thanks for being here with us today. I would like to start this presentation by recollecting together a point in the plot of The Lord of the Rings when Gandalf the Grey had to face an incredibly dangerous enemy, the Balrog. And against all odds, he was able not only to survive the battle, but also to recover and come back stronger than he was before as Gandalf the White. The ability to recover from errors and in an automated way is what defines a resilient system. Resilience requires a lot of planning in different layers of your service, which is infrastructure, business logic, data storage, networking. And in distributed system, failures can be originated both inside a specific service or component, but also in the communication between one service and another. Foreseeing and prevent failures is very hard. And when you have a lot of traffic that impacts your service, that's the moment where you really don't want failures to happen. Traditionally, failures happening on loads are caused by a set of circumstances. The moment that an HTTP request hits a specific host, a set of resources, both hardware and software, needs to be allocated, like CPU or memory. In AWS, this host might be an EC2 instance. The problem comes when a lot of HTTP requests hit the same host. Eventually, those resources will run out, causing the downtime for your service.
Thank you, Sarah, for that introduction to what is resilience. And welcome everyone to this talk, You Shall Not Fail in the Face of Turbulent Conditions. So a quick introduction for me and Sarah. So my name is Yantrey. I'm an AWS Serverless hero, and I've been running production workload on AWS for more than 10 years now. The last couple of years, I focused primarily in the serverless space. Nowadays, I spend half my time working with Lumigo as a developer advocate, and Lumigo is a troubleshooting platform for serverless applications, which make it easy to troubleshoot even complex serverless environments. The other half of my time I spend working as an independent consultant, where I work with companies from all around the world in all kinds of different industries, where I help them go faster by adopting serverless technologies successfully through trainings, through consulting, and sometimes working on projects on behalf of my clients to help them deliver MVP or a new product quickly.
Hey, my name is Sara. I'm Italian and I live in Amsterdam, the Netherlands. I am a backend engineer for The Zone. The Zone is an OTT platform that streams sports events in real time and on demand. As a backend engineer, I contribute to the design, the development, the provisioning, and the monitoring of microservices that power the core functional logic of the platform. In my free time, I'm also director of tech for Shisha, which is a non-profit in Amsterdam that fosters diversity and inclusion in tech. So we started our presentation by mentioning how traditionally traffic and loads would affect our service. In the case of Lambda and serverless, things work a bit different. The moment that an HTTP request or an event hits your Lambda, a specific isolated execution environment on a Lambda instance is spins up. That Lambda has its own container resources, like for instance memory, and it's completely isolated. So that means the moment that a new invocation occurs, a new isolated execution environment spins up. Redundancy of computing units is one of the patterns that contribute to the resilience of your service. When you create one API gateway and one Lambda, those services are created in a region in multiple geographical locations, which are some availability zones belonging to that region. The benefit of such situation is the fact that you no longer have one specific point of failure which is in one availability zone, but if one availability zone goes down, the other ones can take over. Also, traditionally, when you have geographically distributed computing units, you would have to set up a load balancer to make sure that the load gets spread evenly across different locations or different computing units. That is no longer a problem when you have a API gateway, because you just hit the API gateway endpoint, one endpoint, and the traffic load is handled for you out of the box. Data replication is also an important pattern to improve resilience and availability. That because if one availability zone goes down, the other can take over. So AWS, in case of DynamoDB, syncs all the data that you have inside an availability zones to the other availability zones under the hood. You don't need to take care about it. And that's great, because that means that your service will be, the data storage will be available at any time inside a specific region. Let's have a look at the way the Lambda handles traffic. The concurrency of a Lambda function is the number of concurrent instances that that function can serve at a specific time. Apart from this limitation, the Lambdas can scale up to 500 instances containers each minute. The concurrency limitation that I mentioned above can also vary between region to region according to where you create your own Lambda. If your the total number of invocation goes over that specific limitation that I mentioned, which is represented by the violet area in the diagram, then Lambda will throttle the event. And if it's integrating with API Gateway, that means that API Gateway will return an error to the client. A new functionality that came out recently, last year, is the Lambda provision concurrency. The provision concurrency is a limit that you defined and it's a number, and that number will represent the number of pre-initialized instances that will be pre-warmed in the moment of the invocation. The benefit of provision concurrency is the fact that you are underneath, so below that limit of concurrent execution environment being spinned up, below that number, you no longer will have a Lambda cold start, which is a very common situation for AWS users. But also you will no longer witness burst limits. However, over that limitation, you will have to face both problems again. A way to overcome this, especially if you have traffic spikes of traffic that are not very predictable, so you cannot really provision in advance, is to integrate provision concurrency with an application autoscaling. You can do that by listening to AWS CloudWatch metrics. So an alarm in CloudWatch will trigger a change in the provision concurrency limit, so that will raise or lower the limit according to a specific set of metrics that you can integrate and listen to. If you don't pay a lot of attention about this limitation, the risk is that the Lambda will throttle your request, causing downtime for your consumers, and that's not really optimal. But how do we solve this? The answer is, it depends. First of all, you need to make sure that if you are in charge of the client side of the application, you always implement retry policies, because the throttling can happen on different layers of your own application as well. It can happen in Dynamo, it can happen in the Lambda service, and in the API gateway as well. So let's have a look at a scenario where the client of your REST API application only needs an acknowledgement. One way to mitigate that is to integrate SQS with API Gateway. So the moment that you have a new request coming in, API Gateway will dispatch the event to SQS, returning to the client an immediate response, that event is forwarded to the Lambda, which does some asynchronous event processing that takes maybe a longer time. However, sometimes this is not possible because maybe the client needs to have something more computed, not just an acknowledgement. So let's see. There are some scenarios around that. So the first scenario is you have predictable spikes. So you can predict the moment when you have a lot of traffic coming to your service. That scenario is typical to e-commerce website and application. So for example, in case of Amazon, when there is a Black Friday, Amazon can prepare and pre-provision their services to get ready for the traffic. In case of Netflix, the traffic spike can occur during a new series launch that has been announced for a long time through marketing. Or in case of the Zone, that might mean that might happen during a sport event that is being live streamed. There is a scenario that is harder to handle, which is when you have unpredictable spikes. Those spikes are usually generated by user actions, and this is typical from a social media platform. An example would be some time ago, Jennifer Aniston from Friends. She published her first picture on Instagram, and by doing that, she brought down the platform for everyone, which is insane. What are the mitigations for these sort of scenarios? In case of REST API, one solution would be to use one Lambda for each endpoint. So if you have multiple endpoints integrated with the API gateway, make sure that you use one endpoint for Lambda. The advantage of that is not only that you spread the Lambda concurrency limit and limitations among different Lambdas, but you also have different IAM roles with more granular policies. And that means that if a Lambda needs only to read on a global DynamoDB table, for instance, then that Lambda has permissions only to do so and not to write and read and do all sort of things. And it's also better. Another mitigation would be to raise the limit with an AWS support ticket. It's very easy to do so. You can do that via the console. Some limitation can be raised, some not, but it's a possibility and it doesn't take a lot of effort, so that's possible. Another way is to optimize the performance. So lower latency means a better concurrency being handled. And one way to optimize performance is, for instance, if you use Node.js to reduce the size of your artifact. So make sure that your node modules is not as very big, so as small as possible. Another way would be to, for instance, improve the way the TCP connections are open in your Lambda. So make sure that your HTTP agent in Node.js opens one TCP connection. So reuse the same TCP connection for similar HTTP request without opening one TCP connection for every HTTP request. That has adds a lot to the latency. Also, increasing the Lambda memory sounds like more expensive, but sometimes it's better in terms of performance and in terms of costs. Offloading computing operation to asynchronous flow is also another way to mitigate this sort of problem. So for example, let's assume that you have a Lambda that does a lot of computing. In that case, you can return a faster response to the client and offload that operation to an asynchronous flow where with SQS, for example, which is a very cost-effective solution. And this could be implemented, for instance, when you have a subscription, you have to create a subscription for your user that just registered. You want to return a response to the user, allow the user experience to be smooth and seamless, and then in the background handle the subscription generation. Last but not least, you can use provision capacity plus autoscaling. The autoscaling part is especially important if you don't know when your traffic will be generated. So as we mentioned before, you can integrate the provision limit together with CloudWatch metrics and alarms. Just a reminder, beware of long timeouts. So when you create an API gateway, the default timeout in terms of seconds is 29, which is very high, and that's not very optimal. So make sure you fine tune that. Also, another thing that you should probably be aware is that when you integrate SQS with a Lambda, always make sure that the the SQS visibility timeout is higher than the Lambda timeout. Until now, we only and especially looked at single region architectures, which are great, are very simple, straightforward. However, if your application has a high availability requirement, that means that if your region goes down, if there is something is wrong with your regional stack and your regional stack is not available, then your whole service isn't available. And that's again another single point of failure. That's where multi-region architecture take over. Multi-region architectures means that you deploy your service in multiple regions. The easiest pattern, if we can call it easy, is the active-passive architecture. When you have active-passive, you have one active region, which is the only region that receives the traffic, and one passive region that does nothing. It just exists. You can implement this pattern in Route 53 with failover routing together with Route 53 health checks that ping constantly the regional stacks, both of the active and the passive regions. If the active region becomes unhealthy based on these health checks, then the passive region take over and the traffic is no longer sent to the old active region, but gets sent to the passive region that is promoted to new active. Another pattern is active-active architecture. Contrary to the other one, in this one, both regions or multiple regions get traffic at the same time. The criteria of which traffic goes to which region depends on your routing policies that you implement in Route 53. It can be based on latency, it can be weighted routing, so 50-50%. It can be geolocated. So contrary to the last one, both regions receive traffic. Something that needs to be taken into account when doing active-active and data replication at the same time is beware of replication records. So let's have a look at this diagram. You have a REST API that is deployed in two different regions. They are both active-active, so they are receiving traffic. And you have both regions writing to a global DynamoDB table with specific records that get added in that specific region. When you add a record in a region in a global DynamoDB table, for example, that record gets synced in the global DynamoDB table that is in the other region by AWS. If you implement, for instance, data reporting for the DynamoDB information, you need to be careful about discarding replication records that you get from the streams of records generated by the DynamoDB changes. So make sure you take care of that and you distinguish what are the replication records from the records that are actually the new changes coming from the regional stack. So we saw some patterns that are related to multi-region architecture because, as we mentioned before, data replication and redundancy of computing units, even from an availability zone perspective, but now from a regional perspective, mitigate failures, because you no longer have one single point of like one vulnerable point, but you have redundancy, so that allows protection against the regional failures, and that's a great benefit in terms of availability and resilience. However, that comes with a lot of complexity. It's very, very hard to implement, and it takes a lot of time, um, both about in terms of development, but also in terms of provisioning and make sure that everything works correctly. And that is the pain point. When you implement health checks that are that are evaluating the health of a specific regional stack, it's very hard to test. It's very hard. And that's when Jan comes in.
Right, so complex systems are difficult to test, and I think the best way we have for testing these complex systems is chaos engineering, which many of you may have heard about from the likes of Netflix or Amazon, talking about how they will kill their servers in production randomly to simulate infrastructure failures that result in the loss of EC2 servers, and see if the system can still stay up when those infrastructure problems happen. It's certainly one way you can apply the principles of chaos engineering in practice, but chaos engineering itself is much broader. And in the words of principles of chaos.org, which is easily one of the best places you can go and read about chaos engineering if you want to get started and understand its core principles, it defines chaos engineering as a discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And it's becoming more, I guess, increasingly important to many organizations around the world because we're just building more complex systems now, which have more complex and difficult to predict failure modes. And the thing about failure is that, be it hardware failure or software bugs, you can't choose when they happen. The moment chooses you, and you can only choose how prepared you want to be when they do happen. And the goal of chaos engineering is to identify weaknesses in our system before they manifest into system-wide aberrant behaviors, because we have failed to identify these systemic weaknesses early. And we do that by using controlled experiments to learn about how our systems actually behave when failure conditions happen. In the same way that we write tests for our business logic, we need to test our system's robustness and resilience against the turbulent conditions that it is going to face in production. Failures are inevitable. The only thing you can choose is how prepared you want to be when they happen. And the two primary ways of doing this is through organized events such as game days, where, for example, you gather together as a team and one of you would turn off, say, networking on one of your servers and see how quickly your teammates are able to identify the problem and resolve it, to see whether or not you have sufficient monitoring and diagnostic tools in place, or by programmatically injecting failures into the system to see how it actually handles them. Of course, you want to do these experiments in a controlled fashion so that the experiment doesn't just spiral out of control and actually cause an outage in production and end up affecting your users. And there are lots of different things you can do to keep the lid on the experiment and keep it under control. We're going to talk about this in a bit, as it's quite an important topic when it comes to chaos engineering. But first, the 4 steps for you to start doing some chaos experiments yourself. Step 1, you got to know what normal looks like in your system. If everything's on fire all the time, then you just don't have a steady state, and you need to get your house in order first and establish what normal working condition looks like. For example, normal may look like the 99 percentile latency is below 500 milliseconds, and that there should be less than 10 HTTP errors per hour, or less than 1% of the requests end up with non-H200 HTTP status. And once you know what normal looks like, then you can start to hypothesize what's going to happen if something was to go wrong. For example, if one of the servers dies, or what if DB starts acting up. And then you can inject failures into the system to simulate those conditions you want to test, but keep them realistic. It's really easy to get carried away once you start doing these experiments. And finally, after you run the experiment, go through the data to look for evidence to prove or disprove your hypothesis. by looking at the metrics, the logs, the X-ray traces, or any other forms of telemetries that you're collecting to look for evidence that your hypothesis about how your system will actually behave is going to hold. And if you're just starting out, do this in a dev or staging environment. You can learn plenty in those non-production environments. Don't go anywhere near production until you are absolutely certain that whatever failure condition you're trying to test, is going to be handled correctly, because you've done this hundreds of times in those lower environments to build up the confidence before you start doing this in production. Remember, the goal is not to actually break production, it's to identify weaknesses before they happen. You don't want to cause an actual outage that's going to put you on a newspaper because your experiment has gone wrong and you took down your service by accident. It's going to be incredibly humiliating and quite embarrassing, and rightly so, because common sense will have told you to practice this in a low-risk environment first before you go and start killing things in production when you have no idea what's actually going to happen. But besides the risk, you need to understand that the problems that you do find, they're not caused by chaos engineering. The experiments simply review weaknesses that you already have in the system. What the experiments have done is to show them to you before bad things actually happen for real, so that you can still have time to prepare for them. That said, there are risks involved, and even when you are experimenting in a non-production environment, as you can still break those dev and staging environments and affect your colleagues who depend on these environments to work. So you still need to have containment measures in place. Firstly, run the experiments during office hours when people are at work and can deal with any unintended consequences quickly to minimize their impact. And also let other people know what you're doing and when you're doing, and when you're going to do them. Be transparent. Lean on the side of over communication than under communication. And importantly, avoid important business dates. If you are doing streaming live sporting events, then don't do anything before or during the event. Apply common sense and avoid taking any unnecessary risks. And if you're going to make a change, then make the smallest change possible. So if you're going to inject some failures to some HTTP endpoints, then inject failures to one API endpoint at a time, and if possible, to just one request at a time. And lastly, have a rollback plan ready before you even start. In case the chocolate fudge hits the fan and you need to stop the experiment quickly and roll back any changes that you've made so far. And I cannot say this enough. Do not start in production. I mean, you can learn an awful lot in those lower environments, and by the time an experiment is graduated to production, you should be very, very, very confident that the system is going to handle it. And you only get to that level of confidence because you've done this hundreds of times in those lower environments already. And the great thing about chaos engineering is that it's not limited to just your application. It can be applied to test your infrastructure, to test the platform, as well as the people and processes that you have in place inside your organization through things like the game days we just described. In terms of tooling, you've probably heard about Netflix's Simian Army, where you have a bunch of monkeys for killing servers, for injecting latency, for killing a whole availability zone, or even the entire region. And nowadays, you also find tools that allow you to run chaos monkey logics through a Lambda function, so you don't have to run a server to occasionally queue other servers. But what do we do about stress testing and chaos using chaos experiments to on our service architecture itself? I mean, we don't have access to the servers that are running our code anymore, right? So there's no server that we can actually queue here. And since AWS is already doing all sorts of experiments to make sure that the Lambda service itself and the infrastructure beneath it are highly resilient. So as a consumer, I don't really have to worry about individual servers dying and hardware failures because Amazon is handling all of that for me. But I'm still responsible for my own application code, and I can still use chaos experiments to identify weaknesses in my application. For example, maybe I've misconfigured my timeouts so that some user-facing API function can timeout if the internal API that is calling have got longer timeout than it does. Or maybe I'm missing some error handling, which is incredibly basic mistake to make, but also very, very common in practice. And in cases where a downstream system suffers an outage, maybe I'm missing a trick here by not having some fallback strategy in place so that I can return some cached or default response, so that I can mitigate the cascade failure where DynamoDB call fails or DynamoDB service having problems, and so my API function having problems, so that my callers having problems and cascade the problem all the way up to the client, so where they get some errors in the app. So Gunnar, who is also a serverless hero as well, he published a very helpful library that allows me to easily inject failures into a Lambda function to simulate different kind of failure conditions. For example, if we want to see, okay, what's going to happen to our app if DynamoDB suddenly has an elevated error rate, maybe we are hammering it too hard and now we're getting those throttled exceptions. Well, we can hypothesize that since the AWS CK has got built-in retries with exponential backoff, then everything should just be fine. And so we ran the experiment where we artificially inject some failures, maybe one of those throughput exceed exceptions, which the SDK should handle automatically and retries. And lo and behold, the function somehow still times out after 6 seconds. So somehow our hypothesis was disproved. And when you dig into it, it turns out that the DynamoDB client for JavaScript defaults to a maximum of 10 retries, and with an exponential backoff starting at 50 milliseconds. And the delay between every retry is calculated using this formula, which Mark Brooker, who is a senior principal engineer at the AWS, professed at the last re:Invent that this is his favorite formula of all time. So when you do the maths, you calculate the maximum delay between every retry, you can see that that delay alone can easily push you over 6 seconds if you just get a couple of throttled exceptions in a row. So it's no wonder that our function timed out. But the big question is, well, we know a weakness here. What can we do to improve the application so it becomes more resilient in the future? We can override the default configuration and set a more reasonable max retry count for our function. And we can also add some fallback as well. Say for reads, we can fall back to a previously cached response, which can be done in the function, or maybe some static default response, which we can also just bake into our application. Or maybe we want to use some kind of shared distributed caching layer using Elastic Cache or something like that. For writes, we can also queue up the write itself. If we couldn't write to DynamoDB directly, we can queue it up to SQS queue or something like that, so that it gets retried in the background afterwards. So the outcome is that we still end up with a more resilient application, which is exactly what we're looking for here as a result of doing these experiments. So all right, let's try another experiment. What if a service that we depend on is having an elevated latency because it's running on servers and its resources are being exhausted, so it can't respond to requests quickly? Well, we already have some retry cache around those API calls, so the hypothesis is that we should handle it just fine. So we run the experiment, and what happens? Well, the function still times out after 6 seconds. I mean, geez, we're just not very good at this thing, are we? So what happened? Turns out we have a mismatch of timeouts here. Most of our functions defaults to 3 or 6 seconds timeout because that's just what the SAM framework or the server framework defaults to. I mean, API Gateway has got a hard timeout of 29 seconds anyway, but most HTTP client libraries are not designed for this serverless environments, and they default to timeout of 60 seconds. So our functions are going to time out long before the HTTP request itself. And the simple fix here is to just align those timeout settings, right? But the big question is, well, what timeout value should you use? I've seen two main strategies for this. One is you can divide the function's timeout equally across the number of HTTP requests you're making. So in this case, our function has got a 6-second timeout and it makes 3 different HTTP requests. So every single request gets 2 seconds. But then some requests might get timed out, even though it would have been fine if we have just let it run because there's enough time in the 6 seconds to actually finish all of them. So a second strategy takes a more optimistic view, and every request gets the full 6 seconds, but then our function ends up timing out even though none of the requests took too long, because but collectively they took longer than the 6 seconds that we had. Luckily for us though, when it comes to Lambda, we can find out how much time is left in the current invocation using the context object, which has got a method called get remaining time remaining in millis. So a better strategy would be to set the HTTP timeout based on how much time is actually left in the invocation, but reserve some time at the end so that you can do any recovery steps like logging the timeout event, publishing custom metrics, or fetching a cached response from somewhere. I mean, that way, every request is given the best chance to succeed, to complete. But if they do end up taking too long, then we will still time them out before they cause the invocation itself to timeout, which in the case of API functions will return a 502 to the caller and cause the error to cascade, which is not what we want. Again, the result of all of this is having a more resilient application, which again is exactly what we're looking for here by doing all of these chaos experiments. So that's it. I want to do a quick recap before we let you guys go. And so today we talked about common failures you find in a distributed system, and the fact that with Lambda and serverless, you get a lot of resilience out of the box because you just get multi-AZ out of the box. And the good thing is you don't have to pay for those extra redundancies because you only pay when your function runs. However, even when it comes to Lambda, you got to think about timeouts because there are a whole bunch of different timeouts. Not all of them are perfectly aligned. Like API Gateway has got 29 seconds integration timeout, but your function can run for up to 15 minutes. We also talk about some common mitigation strategies for dealing with failure modes that's associated with spikes in traffic by offloading non-critical work or non-urgent work into a queue and to them in the background instead, as well as some other mitigations around optimizing the performance of your function and using provision concurrency to avoid having to hitting those auto-scaling limits. And also the gold standard when it comes to building a highly resilient serverless application, which is to go multi-region active, which luckily for us, if you're using fully serverless components like API Gateway, Lambda, and DynamDB, it's actually fairly easy to implement such a system. I want to leave you with this nice quote, which I think really struck a chord with me, that you don't choose the moment being when something fails in production. The moment chooses you. You can only choose how prepared you are when they happen. And for chaos engineering, you can apply them to infrastructure, to platform, your application, as well as to your people and processes in place. And the great thing about using serverless components is that Amazon is already doing that for the infrastructure and the platform. So you can focus more on your efforts on your application code and the process and people you have in place. So with that, thank you guys so much for your time today, and now enjoy the rest of the conference. I hope you guys stay safe.
Hey, thanks everybody for being with us today, and goodbye. See you. Bye bye. Ciao.